I wrote all this stuff down for you so you don't have to take detailed notes. We'll be downstairs. You can pick up the book. Hi. Nice to see you today. Thanks for coming out. John Handler. I'm a Senior Principal Solutions Architect, and I work for AWS. You know, ever since I was a long-haired, bearded undergrad, I studied language and philosophy. And language, to me, it's always been fascinating how language mediates between concepts and people, how we communicate between ourselves via language. And of course, search is a very aligned problem there. You come with some kind of query. It's language that we use to figure out. The search engine uses language to figure out how to match and how to bring you the right stuff. So, you know, I wrote down and sort of thought a lot about how in the present day when we have all this Gen AI, right? And language. It seems like language, again, you know, advances in language are really bringing us to a new kind of frontier. So ever since we started writing stuff down, we started cataloging that stuff. If you go back to ancient Sumeria, the bureaucrats were writing down, or well, with cuneiform, were taking notes about crops and sort of taxes and that kind of stuff. And they actually built indices to keep track of all of the tablets that had this revenue information. You go to the Library of Alexandria. In 245 BC, Callimachus wrote the Penakes. This was a scroll that said, where are all the other scrolls, right? As Mukul was saying, in more modern era, we have card catalogs, where librarians and library science has helped us organize information and make it available. But, you know, a card catalog is sort of static, hard to use, and for the best results, you kind of need to talk to the librarian. I don't know if any of you have ever used a card catalog. You go to the library, there's 10,000 drawers, there's cards all over the place. It's organized in some way that makes sense to a librarian. It doesn't make sense to you, right? So you ultimately go talk to the librarian. Why? Because language is how we do this kind of searching. And of course, you know, Gen AI, right? So what's really happened is we've come to a culmination of kind of decades of research in natural language that have made it possible to have almost conversational interactions with our information systems. And on the plus side, they're scarily good. Like, I assume everybody has played with a chat application, and you type some stuff, and the thing seems like it really understands you. And I want to be careful to put all of this in scare quotes, right? Understanding, concepts, meaning. I think all of those are really human relative terms. But it sure acts like it has those things, right? And that makes it really amazing to use these systems. So in the world of search, we have the kind of 10 blue links, one-shot interactions that we have with our search engines, right? Is language going to take over all of that? No, frankly. If I'm looking for a particular plumbing part to fix my sink, I'm not actually going to want a natural language conversation about that. I want to type what I want, and I want to get it, right? But I think we are headed in a direction where 10 blue links is not going to be the only thing, where we have these more conversational interactions with the technology that will be a lot like talking to the librarian. And they'll extend beyond this one-shot interaction. So to put our brains around kind of all of this, let's start with lexical search. And really, lexical search is about decomposing language in a way that makes it matchable and that preserves the meaning behind the words to bring relevant results based on meaning, right? So somebody comes to a search engine, they have an information goal, they have some window through which they can provide their information goal. Texts, facets, geo-information, other ways that they can bring information in, we have our search engine, OpenSearch. OpenSearch's job is to compare what that user specified in that kind of terminology with the pile of stuff in its catalog and figure out some stuff that it can bring back that is ranked in some way that matches the information goal, right? In order to do that, we first, as people, we structure our information. We put it into a format where we can add labels on particular pieces of information, where we have text blocks that we can break up, we'll see. And that gives us the basis for matching. Text analysis is a toolbox of methods that we've built or developed to preserve meaning while cutting up big blocks of text into matchable pieces, right? So as an example, Miss Kobayashi's dragon mane Toru cosplay dress outfit. I pulled this one out of the Amazon PQA dataset. If you're not familiar with analysis, that's the analyzed piece of text. So Miss Kobayashi, dragon maid, Toru, blah, blah, blah. We apply stemming to bring words to a common form. And again, here the idea is we're preserving meaning, right? So if I have run, runs, running, those all mean the same thing. So I stem them together to bring all of them into a single matchable term, right? Stop words remove stuff that doesn't mean anything, really. A and the doesn't mean anything, we throw it away. We have synonyms. We add, again, additional words that are conceptually related, first, number one, like that, so that that piece of meaning is preserved, right? All of them working at the token level to improve the matchability, right? And to sustain the meaning through it. Lucene indices, probably all are familiar with this. We have a document, it's a set of JSON fields. They have values. We pass the values through this analysis phase, and that gives us a set of indices where each word that's in that block of text is matchable itself. We have the set of documents where that matches. So here's an example for lexical search. We have our Miss Kobayashi dragon maid outfit, and we have a very soft silicone vinyl stuffed PP cotton body baby. So it's a doll and an outfit, right? We can use the query cotton washable clothes, let's just say. So the first thing we do, we have to analyze the query. We want the terms to have the same format as the text block. So we take cotton washable clothes, it becomes cotton washable cloth, right? Then we go through a term matching process, and we look up cotton washable cloth. We get the posting lists, and if it is an AND query, we go through a merge phase where we're saying it's A and B and C, and to save you a little mental effort, number 38, the baby doll is the one that comes out, right? So because of this, we actually use an OR instead, and we rely on ranking to bring the right stuff to the top. So if we do OR, then number 22, the Miss Kobayashi outfit, comes out, right? We have our rank function for lexical search, BM25, and the key idea being we're going to look at the number of times the words appear, we're going to look in that document versus how rare are they across all the documents. Again, like at a language level, what we're trying to do is pull out the differentiating terms, the meaningful terms from that query as far as it relates to our corpus. We do a bunch of other stuff, term saturation, document saturation, like we do some statistical manipulation to kind of make it come out okay. And that's how we decide which one matches, right? So coming back to sort of the main thread, we start with a query, we get some results, maybe we're happy. If we're happy, great, we found it. If we're not happy, well, we may be frustrated and we give up, right? If we're not frustrated, we go back and we try another query. So this is this iterative, one-shot kind of matching that we do when we use search engines. We don't carry any context through. It's not a conversation. This is a set of individual tasks. Now, having said that, yes, we can carry conversation through. Yes, we can bring context through. But conceptually, it's a one-shot, right? To go beyond that, you have to go beyond single terms, right? You have to maintain this contextual context. You have to bring in additional information. Which brings us to vectors. So I'm a search guy. I'm not an ML guy. So like all of this stuff, people are talking about vectors, and we're going to use vectors, and it's going to be really cool. I don't know why that works, right? So, well, I didn't. So I have some potentially thoughts on that, right? So some ML models, and they're called large language models, they deal with language, they can capture the meaning of words or text, right? They emit vectors with values in many dimensions, and where related concepts cluster together. Still in the back of your head, quotes around meaning and concepts and all that stuff, right? So how do they do this? So what is a vector? Everybody know what a vector is? Yeah. It's a quantity. It has a magnitude and a direction, right? In 2 dimensions, you can represent a vector by 2 coordinates, 4, 6 in this case, for this particular vector. But those directions, they could mean anything, right? For instance, the y-axis could be orange, and the x-axis could be red, or fruit, rather, or apple, sorry. If I then want to represent apple, my vector looks like a big value for the apple axis and a 0 for the orange axis, or, conceptually. So that is the idea behind one-hot coding. So I have a set of dimensions that is the same as the number of words that are in my corpus, and I put a 1 for each word, right? It's useful. Many ML techniques actually use this, and this is a good way to code stuff. Its drawback is it's a little bit limited for generalization. I can't really say red plus fruit equals apple, because apple is coded somewhere else, and red and fruit are coded over here. The vector red plus fruit doesn't mean anything, right? So generalization is a little limited. If we relax a little bit and talk about a more sparse coding, in sparse vectors, we have dimensions that are much less than the number of words in the corpus, typically around 30,000. And those vectors are the terms, the vocabulary for those vectors is actually a mashup of the terms that are in the original words in the corpus, right? It does allow us some generalization because as we're pushing terms together, we're actually squashing together some of the concepts based on the co-occurrences of those terms, right? But we maintain a close relationship between the original terms and the values that we use for the sparse vector, right? So sparse vectors on the spectrum look like one-hot, then sparse, then we get to dense, right? So the idea behind all of this, again, relates back to the axes and how are we labeling the different axes to provide values, right? Idea behind dense vectors, this is an example, select a few concepts. We have red, fruit, and yellow. So apple has values on the red and fruit dimensions. Pineapple and banana have values on the yellow and fruit dimensions. And we can code, as we add additional axes, we'll add additional ways to code information, right? We add capacity. So how do we decide what these axes are? Well, we use neural networks and backpropagation to discover, if you will, the axes. And that is what large language models are doing when they are training. They're figuring out what are the dimensions and how do I pack the words into those dimensions as vector values, right? In a sparse model, dense model, dimensions much less than the number of words in the corpus. And this is actually much less than sparse as well. So dense models tend to emit vectors in the 1,000 to maybe few thousand range, sometimes 100. So it's much less. That's an example of a dense vector. Not that it really means anything when you look at it. The generalization is high because, again, we've squashed down a lot of information into a few hundreds or thousands of dimensions. So our ability to generalize is really good, but it brings with it bad generalizations or hallucinations, and we have to work to keep those out or overcome them. Language itself is complex and nonlinear, and so the space that we're trying to model is complex. We have, if we had a line in this many dimensions, we would have an equation that looks like a bunch of coefficients and a linear equation, right? Well, what backprop learns and these large language models need billions of parameters in a highly nonlinear function to model that space. So that's what they're doing. I wanted to touch on and clarify some of the terms. So a model for ML is simply a function. It maps an input to an output. So there are all kinds of ML models that are not large language models that can, for instance, take an image and map it into some vector space, right? It's not an LLM. In the Gen AI craze, everybody is getting all excited about LLMs. They're not all LLMs, right? They're just models. Embedding models generate vector embeddings as their output, right? So it's a large language model, generates a vector. Foundation models are trained on large amounts of data, the whole internet. You can fine-tune these. We have multimodal models that can take images and text. We have generative models that generate new content, right? So it's a text generator or an image generator, right? All right, so that's how we go from language to vector representation. So how do we go from vector representation to matching in search? There's a number of different ways that people are doing this and adopting. So sparse models provide us, again, almost a direct way to query token to token. It's close to token to token. People are using sparse. Mukul talked about sparse actually works really well for very mixed kind of cases where you have both semantic and token type queries. Multimodal is the ability to bring more than one modality of information to your query. I can query with an image, I can query with a piece of text, I can combine them, and that gives me a way to retrieve what I want. Hybrid search is being able to run both lexical and vector search, combine those results, again, improving overall the retrieval. And yes, Gen AI is a thing. As ML capabilities continue to improve, I think that interaction is going to be there, not the 10 blue links necessarily. So we're saying similarity a lot, and OpenSearch's job is to go find what's similar in its catalog to what the query is. We have a couple of ways. We have text-to-text, this is lexical search. We have vector similarity that we talked about, and we have user behavior, which I haven't talked about and won't talk about, but is a super important component of similarity. If, as an e-commerce application, if my application knows that I love Adidas shoes, that's a really important input to the search problem, right? So there's the Learning to Rank plugin, and we have all kinds of efforts on bringing in user behavior and improving search that way. Just not going to talk about that today. So what does it mean similar? We can try to visualize this really highly dimensional vector as a two-dimensional picture. It's kind of hard. It loses a lot in the translation, but the core idea is things that are similar get similar encodings, and so where their location in that big space is close together. And close means either Euclidean distance or cosine distance, Manhattan distance. There are various distance metrics that you can use to measure the closeness of two vectors. The score for a document, when you're using dense vectors is the distance from the query to the document point, right? So the neural plugin helps with bringing together the text and the vectors, creating the vector for the query, and running the whole query. If you were doing it manually, you would, on indexing time, you'd take your source document. Usually you produce chunks out of that document because the vector embedding models don't really take more than 100,000 or so chunks. So you would chunk it all up into small pieces, or maybe you would summarize it with an LLM or something like that. You'd send it off to some model hosting service like Bedrock, and then that would send you back an embedding vector, which you'd put in the document and index it in a KNN index, right? On the search side, you have to create the embedding. Again, you send the query off to your embedding model, you get a vector back, you put that into a KNN type query, and that gives you a distance ranked kind of scoring. So neural plugin really just takes over the communication with a third-party hosting service. Neural plugin enables you to refer to a model. It then calls out with the chunk to get the vector embedding. It puts it into a field that you specify. How that looks, you use an ingest pipeline to connect your model. You provide a field map that says, hey, this is the field that has my chunk in it. This is the field I want my embedding to go in. Neural plugin just takes care of calling out. On the search side, and this is an example for a hybrid query, we have we define a search pipeline, and then we specify the processors. So we have a normalization processor, and this gives us, when we're going to send the hybrid query, the weighting, the relative weighting between the clauses in the hybrid query. So we normalize and then combine the scores for each of them. Some examples of how this works. So again, Amazon PQA data, sneakers. In this case, we're using a pipeline, which is just doing a regular vector embedding. Our query gets embedded as well, and we run a neural query to get that result. In this case, we are then, what am I doing here? So this is, oh, sorry, sparse. Hello. It is 1 in the morning for my body, so my brain is kind of going, but my body is not caught up yet. So to do sparse, we actually use a sparse model, right? So it's not different on the ingest side. We also use the rank features type of field for the sparse model. And then for the query, we use a neural query. We could just use the model. We could just do sparse this way. One cool thing about sparse vectors, if you saw the example I had, each of the tokens has a weight on it. So to score for a sparse query, we actually can just do the dot product between the document vector and the query vector. And that's actually a way faster calculation to do than the dense distance or any of the approximate nearest neighbor algorithms. So we can use this. It's faster, uses less RAM, and generally provides benefits, something like between 10 and 17% improvement for the beer test versus BM25, and 14% improvement over just dense. I love these numbers. Like, it's true on this particular test. For your use case, you have to try this out and see what kind of benefit you get. Likely, you'll get some benefit. So sparse vectors, really nice method that is coming to the fore, right? So hybrid search, again, we're running both lexical and vector search, and we're using that normalization and score combination to get a combined score back. We have our pipeline here. Again, the technique and the weights, arithmetic mean, 0.3, 0.7 between the lexical and vector. And the query looks like that, hybrid query. We set 2 queries in there. Actually, they can be anything. They don't have to be neural. We can use two lexical searches, for instance, to normalize and combine those. And that brings us a result that, again, looking at comparing to BM25, we see something like a 15% improvement using this hybrid scoring methodology. Multimodal, we mentioned. So in this case, the ingest pipeline has a text-image embedding processor. We specify which field has the image, which field has the text. On ingest, the OpenSearch goes and gets the embeddings for those. On the query side, we use a chunk embedding, a neural query, and we pass in the image and the text. And of course, OpenSearch is a core component of a generative AI application. So OpenSearch provides connectors to third-party hosting services. When you're building your generative AI application, you wire in OpenSearch to improve the prompt to reduce hallucinations. So a couple of examples. These are AWS customers. Site uses it for their automated product tagging, making things more searchable, boosting results. Novartis has a catalog of products, and it's a product kind of search. They use vector embeddings to find related products. Amazon Music uses OpenSearch to search 100 million songs and a billion vectors at 7,000 queries per second. And Amazon Brand Protection queries 8 billion items daily to find fraudulent or infringing items against 68 billion vectors. We do have our demo site, ML Playground, opensearch.org. I recommend everybody goes there. You can play with sparse, you can play with semantic, and see how they work. As I said, I wrote it down. I will be downstairs giving away books. They are free, so come get a book. All right, thanks very much. Oh, I forgot. Okay. Oh, yeah. Should we do some Q&A? Sure.
Yeah, we've got about
10 minutes?
10 minutes plus for Q&A.
Yeah.
If anybody have any questions? I saw this hand first.
Hey, very interesting talk. Thanks very much. It's just a quick question. You said you're more of a search guy than an ML guy.
Yeah.
Do you kind of see that role shifting a bit into more hybrid, or maybe moving even just towards ML?
It is a change that we're going through, right? Now, all of a sudden, us search folks have to be really aware of kind of ML stuff, and it's a whole new body of knowledge to kind of bring on board. I do think that we are going to have to understand the fundamentals of vectors and the fundamentals of machine learned models to build better search systems, right? And to figure out, like, how do we weight these things along with the 100 other techniques that we have to improve search relevance. Some of the conversations I've been having today, we've been talking about, again, if you think about it, already lexical search builds in a lot of expertise about meaning and about how language mediates and brings us the right search results. So we can't ignore all that stuff. And certainly for cases like find me the plumbing part, we can't ignore all that stuff. But we can't ignore the conceptual stuff too. I don't know if you've had this experience. So I have a friend, and we were just out for dinner, and we were having a conversation. And at the moment when he would have picked up his phone and Googled something, he picked up his phone for ChatGPT, right? And I feel like that shift is coming where we're going to be thinking more about talking to or conversing with the technology. And so as search practitioners, we have to be able to at least understand what's going on. That was a long-winded answer, but it was a good question. So,
thank you.
Yeah.
Thank you. Any other questions?
Thank you for the really deep dive, or to some extent very interesting. So my question is, how can, I don't have a good answer, so how can we leverage semantic knowledge in a domain space which has rules and domain business logic which is not directly, cannot be embedded directly from the text, but it has to be somewhere represented, maybe in a graph or some technique?
Yeah. So a lot of that, I think, my first blush is a lot of that goes in the prompt, right? So when you're prompting the LLM for the response, you're bringing in additional information. That's from the search engine. But you also are bringing in information about the chatbot's role and how it's supposed to provide things. I do think the business logic can go in there. I also think that at the moment, it's not very clear how we put guardrails around these generative systems. And much like with neurons, there's not a grandmother neuron, where there's not one neuron you can point to that says, oh, that's grandmother, right? Same thing with these models. You can't say, well, this parameter, that's the Apple parameter or the grandmother parameter. And so it makes it difficult to model in hard rules, right? Must be this, must not be that. That's on the application side. We have to pass it through another one, maybe like one of the more code generative kind of modules that can look at and generate some skeleton that can be validated that way. I'll just riff for one more second and say the question of validation is one that's really pressing. What I see out there is a lot of people trying it because it's super cool, but not a lot of people understanding how to evaluate what came out, and not a lot of automation around figuring out, well, LLM said this, that's wrong, right? And so both on the kind of governance and validation, those pieces are very unclear for now. But super important thing to figure out. Yeah.
John, may I add to your answer?
Yeah.
So, I'm not John, but I'll add to his answer. I think we're just at the beginning of using the LLMs in search. And the body of knowledge about search and the body of knowledge about LLMs are colliding in a productive way. But there's so much more we can do in so many different ways. Some of it offline, some of it online. To the graph question, for example, taking the RAG model, which is a pretty basic model, simple model, you do search results, then you ask the LLM to process it. Well, what if you ask the LLM, now how can I extract more information about the things that were returned? So maybe there are company names in the results. Tell me the relations between the companies. Is one a subsidiary of the other, and so on and so forth. So, as you know, LLMs can construct code that will extract things like that from other databases, like graph databases. So there's a huge, huge, huge variety of techniques that can be used to enrich the content. We're just scratching the surface. Of course, there's always the trade-off of how much does it cost to do versus how quickly can you get the result, and how good is the result. But there's so many techniques that we should be using in search that even if you go back 30 years to some of the original work for graphs, let's say the relations between results, so PageRank, but also the other technique, whose name escapes me right now, you can do analyses of the graphs between the results. There are all sorts of things. RAG is just sort of the 0th order thing you can do with search plus LLM, and we have a lot more to do.
Yeah, I mean, I think to tag on that a little bit, how we, again, and to bring it back, here, I'll even put my wrap up there. To bring it back to sort of the main thread is, how does language mediate between my information goals and the world out there? And as we have these various models and these various techniques, and as these different methods come together, it becomes like this larger dialogue about how we use these things and how does information itself relate to other information, right? And so building in the business rules and the guardrails and building in summarization and figuring out how to put those pieces together is ultimately where the technology is kind of headed, right? Yeah, I think that's it for me.
I think we had at least, I saw one more.
Oh, one more question. Okay. You're not letting me go. I have 5 more minutes. Okay.
Yeah, thank you for an excellent talk. I think it helps us make sense of all the alphabet soup of all these new technologies.
Yeah.
So I think there are a number of users and customers, I guess, who are very familiar with semantic search. I think just like you talked about how you started. So, and they're trying to dabble into vector search and how to get into that domain. Now, with regard to their clusters and their setup, they have an idea about the existing setup, but then for these new technologies, for these new vectors and so on, what should they plan out and how do they go about doing that? Because I think you're talking about, for example, using models with Bedrock or some other services as well. So how should they go about approaching this problem?
Thank you. Yeah, thanks for the question. How should you think about deploying this technology? So one thing is, everybody's kicking the tires. There's not a clear move to production kind of methodology, so I'll say that. I think that high level, the trade-offs that you look at are between cost and latency and accuracy, right? So if you can have any two, right? You can have a super fast, highly inaccurate, low-cost system, or you can have a more costly, somewhat slower, and then really accurate system. And so the first thing is to think about, what are the accuracy needs? What do I need? Do I need 95% accurate recall? That's something that I'm going to have to plan for in terms of model dimensionality and not using things like product quantization that would bring my cost down and my latency down, but my accuracy down as well, right? So figuring out what is the accuracy that I need is kind of the first important thing. Once you know your accuracy, then you can work towards, well, I have this dimensionality, I have these choices in terms of algorithms, so HNSW or IVF, I have these choices in terms of quantizing vectors or reducing dimensionality that will lose me this much accuracy. That gives me the background of what do I need in terms of hardware and in terms of disk storage, in terms of running those queries themselves. So that's kind of how I would think about it. I think it's critically important that if you want to adopt this technology, that you build yourself a golden set, which is a set of queries and results where you know what the right answers are. Because that's the only way that you can evaluate what came out, is it the right thing? So that's another really important piece that you have to develop to be able to measure your accuracy.